Hello again. I'm John McDonnell. Thank you for inviting me into your home for another 90 Days, our quarterly video report about issues, events, and people important to you and me and our corporation. In this edition, I'll tell you about our plans to launch the long-range MD-12 jetliner. We'll visit our electronic systems company where they've turned a laboratory curiosity into a new product that can revolutionize the laser industry. Then we're off to Long Beach for the sights and sounds of a very special event, the first flight of the C-17. I'll review the third quarter results and cover other subjects in this edition of 90 Days. In late October, our corporation took a major step to improve our competitive position and expand our family of commercial jetliners by offering the MD-12 jumbo jet to the world's airlines. For an aircraft of its size and range, the MD-12 will provide carriers with superior operating economics. In fact, it will have a greater payload range capability than the newest 747 and be about 7% more economical to operate. The MD-12 will be 35 feet longer than the MD-11, have a bigger wing and more powerful engines, and carry up to 375 passengers on routes over 9,000 miles. That's the equivalent of flying passengers and baggage nonstop from Honolulu to Athens or Los Angeles to Bangkok. Its cargo capacity will be the largest of any aircraft. However, many things must happen before we launch the MD-12. For one, we need enough orders to justify production. And to help fund the program, share risks, and offer low-cost, high-quality production, we need partners. Partners who can offer access to markets in the Asia-Pacific region, which has the highest traffic growth in the world. Our discussions include large risk-sharing subcontracts in the MD-12 program, and substantial but minority equity investments in our commercial transport business. By the time you are watching your 90 Days tape, an announcement regarding partnerships may already have been made. When the program is launched, MD-12 final assembly will be done in a new, modern, cost-efficient facility in the United States. McDonnell Douglas is a corporation of remarkable contrasts. At Douglas Aircraft, we build a giant airlifter with a wingspan measured in hundreds of feet. And at our electronic systems company in St. Louis, we build this. It's a microelectronic device called a laser diode bar. The nearly 1,000 diodes on its edge measure less than the width of a human hair. As you're about to see, whether we manufacture giant airplanes or microscopic diodes, the fundamental principles of TQMS must apply. This is the story of how an opportunity to mass-produce diode bars for a commercial customer almost stalled because of a breakdown in communications. The microelectronics people who make diode bars and the laser systems people who use and market them had stopped talking to each other.
Essentially, microelectronics, photonics, is a production-oriented organization that is charged with building solid-state laser diodes. The microelectronics photonics operation is very much like a silicon semiconductor operation, building integrated circuits or any solid-state products.
I'm the director of laser systems. I have the responsibility for tactical and industrial lasers. We make the laser subsystem. We do the production, final assembly, test, delivery, and support. We are the business side of it. The relationship between laser systems and microphotonics is very much a buyer-customer relationship. Dale's people make the enabling components that we take and integrate into the system level. In simplest terms, a laser is a device that converts electrical energy into light. A very high power, very focused beam of light. that's used in dozens of applications and at various power levels. Traditionally, lasers have been built so that it's optical energy that is pumping a host material to emit a light. This, for example, is a host element. This would be the emitter, the thing that puts out light. This is a slab. It's neodymium YAG. It's a crystal material that's grown. What they've done is they take these rods, or flash lamps they're called, and they light them. And it's like putting a strobe light in. As the optical energy entering this slab would excite the atoms and would generate light. These flash lamps have to be changed out periodically, and they're quite expensive. What we have done at McDonnell Douglas is a lot of the pioneering work in diode pumping. We have developed a small microphotonic device that's extremely rugged and does the same job, we think, much more efficiently. These diodes are good for 500 million to 1 billion shots. Essentially, they're there for the lifetime of the system. You don't have to worry about changing them out.
Here you see a diode product that we build. The diode itself is the front face of gallium arsenide that you see aimed toward the camera. The light is emitted out of that face. We stack these individual bars together in a stack that looks something like this. Electrical energy, a current, is placed across this stack of diodes, and that is converted to photons, to light, and the light comes out the face of the diode array. This diode array and several others like it then are used to what is called pump a slab of lasing material. So the diodes are placed near the slab and they emit light into the slab. The slab is excited and in turn amplifies and emits even more light out each end. And that is what ultimately gives you the high power laser product. Well, we have had solid state diode technology around McDonnell Douglas for a number of years. We have had a good technical laboratory capability for some period of time.
I guess you would characterize the laser business for the past few years as almost applied research. It was done by physicists and technicians, and we made one of this and one of that. What always kept us out of the market was the fact that diodes would cost anywhere from $900 to $1,000 each. About 18 months ago, we signed a joint development agreement with a small company called Hampshire Instruments. The computer industry has a need for very fine feature sizes etched on silicon wafers. As the demand for more and more capacity on a chip grows, feature sizes have to shrink. What Hampshire Instruments can do that no one else can do today is produce a machine that will allow them to write these very fine feature sizes. But it required a high power laser. They were attracted to the diode pump laser, so we agreed we would build a pump array for them, and it consisted of about 18,000 diodes.
Well, once the notion that we could indeed engage in a high volume application became solidified with the management, then the task was to take a laboratory scale process and now make it manufacturable.
They came to Dale and said, here's what we need, here's your charge order. And Dale came back with an estimate and a schedule.
Well, from a manufacturing standpoint, bringing up a semiconductor operation, you have to put a lot of fairly basic things in place. And in this particular instance, we had a lot of changes that needed to be made from laboratory scale processes to get into real live productionized processes. And if you don't communicate that regularly with the customer, you can leave them feeling that nothing is happening.
So my guys were seeing the money get spent, and they were seeing the charges come in, but they weren't getting anything delivered. And they weren't smart enough, I thought, to go and ask, what's wrong? And on Dale's side, nobody was stepping forward and saying, hey, here's our problem. So there was a period of escalating tension and hostility almost that had broken out between the two organizations. And very shortly after I got this job, Dale and I sat down and had lunch together, and we agreed to that we had a problem. There was enough rocks being thrown to go widely around. So we did a variety of things. One of Dale's people suggested that we have an all-day technical interchange meeting where the systems guys came forward and explained what they did and why they did it and what the product was used for. And the people who were making the diodes now saw it as not just a component, but as an element of the system, and they understood some of the things that were driving the requirements. We put together several high-performance work teams to deal with issues like selecting a type of package, or there was a problem with soldering these things. So my people and Dale's people began to work together.
I think what happened here is that we finally learned to listen and talk to the customer. A year ago, it was a real struggle to get a few hundred diodes out for a program. Today, we are capable of turning out multi-thousands per month.
What Dale has done over the past year is bring the cost of diodes down closer to $100. Now all of a sudden we have an affordable system. That has been instrumental in our ability to now actually capture contracts because we've got an affordable product.
I think one of the key lessons is that no matter what happens, good or bad, you keep talking. I think the second thing that's probably worth learning by many managers is to have faith in the people that are doing the work, and if they can communicate and you can open up those lines of communication, people will really perform. People will really perform.
As Mike Barnes and Dale DeVries have demonstrated, open, honest, and realistic communication between people and departments is essential to identify problems, fix processes, and improve the quality of work. It can even save the business. Managers must emphasize face-to-face communications instead of firing off memos. They should also be models for open communications. An open-door policy is a good start. Walking around, daily interaction with your teammates helps too. By the way, the people at Electronic Systems are really onto something. Because diode pump lasers require less power and cooling, they promise to be to the laser industry what the transistor was to consumer electronics. And now let's look at our third quarter financial results. Contrary to the negative headlines spawned by congressional hearings, our financial performance strongly indicates we've turned the corner and are headed in the right direction. We had third quarter net earnings of $77 million. Disregarding unusual gains we had from the settlement of certain pension fund obligations, earnings last year at the same time were only $14 million. Net earnings for the 9-month period totaled $212 million compared to $73 million last year, again disregarding the pension fund gains. Especially encouraging is the fact that our higher earnings and aggressive asset management are enabling us to pay down our aerospace debt. We've reduced it by 19% since the end of the first quarter. Looking at our performance from an operating earnings standpoint, earnings before taxes, interest expense, and other costs, we continue to have the highest operating earnings in our history, $643 million through the first 9 months. This is more than 40% higher than the previous record 9 months earnings in 1985. Performance in our segments is mixed. For the first 9 months, combat aircraft had operating earnings of $388 million. However, while earnings are solid, when you compare this year's second and third quarters, earnings are essentially flat. In October, our helicopter company delivered the first of 7 MD-520 no-tar helicopters to the Phoenix Police Department. Acceptance of the new design is very encouraging. There are 164 orders and 21 options for this revolutionary no-tail rotor aircraft. In missiles, space, and electronics, we had 9 months